So good morning, my name's Nick Allott and I'm the CEO of Nquiring Minds. And today I want to talk to you about the consumer IoT attack surface. And what I'm talking to you about today is from the perspective or from the combined efforts of the Many Secured project. I think you might hear about the Many Secured project a couple of times in this conference. But fundamentally, it's a new collaborative research project that contains ourselves, Nquiring Minds, the Internet of Things Security Foundation, University of Oxford, and Cisco. So before we dig in the detail, it might be worth exploring some of the assumptions behind the Many Secured project. So our starting assumption is, and I've used this analogy before, that the horse has already bolted. A lot of insecure devices are already out there in the wild. And the problem that we've faced over and above future-proofing new tech is the legacy containment problem. How do we contain the risk posed by insecure devices already out there in the field? And, the Many Secured project sort of, the name does what it says on the tin, and it's there as a conceptual piece of the architecture, essentially a new gateway component that has the ability to secure many devices, many of the IoT devices that may be already deployed in your home. And I think it's important to understand that perspective before we dig into some of the technical details of the architecture that we're about to move on to. So when we started this collaborative work, we start with a foundational problem, which is when four parties sit around the table. Do we really understand the security risk? And maybe more pertinently, can we describe it in a way where we retain that level of understanding? And having dipped in and out of a number of IoT security initiatives over the past few years, I can tell you categorically, although there's a lot of smart people out there and a lot of understanding of the deep problems, there's a lot of miscommunication that's largely down to inconsistent naming and a lack of a common architectural model. So let's start with the naive question: what is your mental model of the security attack surface? This is very crude, very primitive view, but probably where a lot of people start. I mean, you've got an IoT device that sits behind an intranet, especially in the commercial sense. We've got cloud services, and possibly there's other IoT devices that roam out there in the big wide world. And each of those separate devices has a separate attack surface. So the reality, of course, it's a lot more complicated than this. So what we have on the screen here is our collaborative best efforts to come up with a common architectural view with some common namings for the key architectural elements and interfaces, particularly as it relates to a consumer IoT deployment. So we're not pretending this is correct or perfect, but hopefully it'll form the basis of a number of iterations where we can refine this going forward. And essentially all I'm going to do in the rest of this presentation is step through each of these elements, explain what we mean by them, understand about them, look at the individual elements and interfaces, and identify what is peculiar about each one from a security perspective. So let's start by looking at the IoT devices themselves. So the way we divide up the world, we see two types: the IP devices and the non-IP devices. So these are the traditional IP devices, things like speakers, webcams, temperature monitors, etc. And the conventions we've used here, just to explain, we've used the G notation to represent a whole class of devices. So IID here is the internet-enabled IoT device, and then the coloured rectangles represent the physical interfaces via which connection can be made. So an IP-based IoT device, the principal connection method is IP, obviously the internet one, which is the blue rectangle to the right. But then some may support a USB interface, either for charging or software updates, possibly also Bluetooth devices. So, typical IP IoT device has got, up to 3 physical methods of connection, where, the principal way of talking with it is via internet protocol. So let's keep things simple for now, still looking just at the IP devices, and see how do these devices connect internally. So internally on the network, we've got this other group of entities that we call local user applications. So this could be a PC app, a phone application, a tablet application, and the fourth one on there is another class, which is the voice applications, which is something that might run on Amazon Alexa or sort of like Google Home, etc. And again, assuming, and this is an assumption we'll come back to in a minute, assuming that this local application can make a connection to this IP device over the local internet, there are essentially 2 flavors of connection it can make. We've divided into two connections. We've got the blue F links that we call the functional links, and the red M links called the management links. So the functional link is the day-by-day operation of that particular IoT device in terms of how it communicates its data to this local user application. So for the speaker, it's sort of like the command functions, etc., turn volume up or down, actual sort of play the bits being sent to it. And so, this interface is expected to be used all the time. It has some security implications, but of a relatively pedestrian sort. The M links, and this isn't a perfect distinction, but it's a good enough. The M links we separate out as management links. So these are essentially the administration functions. They'll often require privilege, i.e., you'll have to enter the username and password, and it'll be the mechanism via which you may, for example, update the firmware, make some fundamental configuration setting, change a server setting, etc. So, what we have here already is a relatively simple sort of like day-to-day use case where an application on a phone or a tablet or a voice application is interworking with one of the IoT devices, principally by the blue-coloured sort of like IP physical interface. So let's bring it up a level and start looking at some of the cloud components, and try and contextualize it against some real-world examples. So let's take webcams as a starting point. Webcams, as you know, we could choose to connect directly via a local PC application, possibly local internet, or probably more often than not a mobile phone application. But webcams, as we know, often, whether you ask them to or not, decide to talk directly to cloud servers wherever they may be, China, America, or what have you. And the point here is, from a security perspective, especially when it comes to these management interfaces, the ones in red, this is all the difference in the world. If you are supporting like a management interface over, for example, like Bluetooth or USB to update the firmware, that's one set of security exposures. But if the webcam is electing to connect to a cloud service and then possibly offering firmware updates over that mechanism, it's an entirely different risk profile. So that's one example. Now let's move on to speakers. So my house, I have some Samsung speakers. How many different ways could I connect to them? So my Samsung speakers actually do include a Bluetooth interface. And sometimes that is the mechanism by which I want to listen to music via my mobile phone application. Yeah, but increasingly there's more sophisticated options. Some of the speakers offer the ability for web servers like BBC iSounds or YouTube to connect to it over the internet, which is essentially via this method here. Or sort of Spotify, for example, is doing some strange form of local discovery between, Spotify is a local user application. It's a mobile phone one. It's discovering that speaker capability and then streaming those bits over. That's another mechanism. And then, like at the other end of the spectrum, also at home, I've got some Alexa speakers. So this is, I think we'll dig into this in a minute, but this starts to get quite interesting in terms of how these different sort of like speaker interfaces and speaker modalities connect. The typical way of connecting between the speaker and Alexa is essentially via my mobile phone app. Now, other apps and services can use that Alexa speaker, but it's usually then via that mobile phone app. But there's lots of strange anomalies. So I don't know if any of you have tried this, but I tried setting a timer on my Alexa speaker the other day when my internet was down. It was somewhat surprising that it didn't work and it wouldn't work, because what that is implying that is when I give a voice command to my speaker asking something simple like set a timer, which has no obvious external dependency on the internet, it doesn't work at all. So what's actually happening in that case is there's a round trip going between the local application to the speaker, and then the speaker up to the cloud service, and then back again. So the reason I sort of like put these slides up there is just to start to explain how even some of the most simple and most obvious IoT use cases, there's a lot of very subtle complexity going on behind the scenes. And we really need an effective language to be able to describe it such that we can understand why is this speaker or this IoT device operating differently to another one, and also, and importantly, then be able to understand what the implications are from a security perspective. So let's color in some of the details. So what I'm showing on screen now is the output of a program called Fing. So if you haven't used Fing, I highly recommend it. It's a very well-designed, simple application that does internal network scans and port scans on your internal device. It allows you to come to a very sort of like quick and real understanding of exactly what you've got on your network. So this just happens to be what was on my network a few minutes ago, and it's probably at the more sort of like techie geek end of the spectrum, but are not a typical sort of like setup for a household. I've got my sort of like main Virgin router here. It's the ARIS one you can see on the screen here. There's a number of things that think they're Amazon Fire Sticks. They're not. They're actual Amazon Alexa speakers, which is these ones here. I happen to have a NAS drive on the network. And I mentioned also earlier I think it's called a WAP Tigger thing here. So this is the Samsung speaker. So home media setup for a reasonably sized house with a number of different sort of like technologies. There's another thing here that I want to draw attention to, because we'll get onto this in a minute, which is these things. I've got a Wi-Fi network extender. And there's a home plug extender here. And we'll come back to those in a minute. So one of the important points I want to make here is you can click on pretty much any one of those devices, especially those ones calling themselves IoT devices. You can do an IP port scan, and it will tell you, what IP interfaces are open and external. And in 9 times out of 10, you're going to get some services exposed on this one here, HTTP port 80. So, on the diagram before, what this means is this IP interface is open on one or more ports, There is what amounts to a management interface, because most of these are management interfaces. They allow you to do quite some sort of like detailed security privilege functions on there. But the key thing here is that's an unencrypted port. It's unencrypted internet transport. So here's a real one on my network. It's the TP-Link extender. That's the IP address here on the top left. And the important thing is this: not secure, unencrypted. So what does that mean? That means if you look at all of the current IoT security guidelines about, please do not use default passwords. As it stands at the moment, you can have whatever password policy you like, but fundamentally, most IoT devices is irrelevant, because every time a local client tries to connect to it, it's doing so over an unencrypted piece, internet protocol, and any number of attacks are possible, from erroneous IoT devices to physical human hackers to applications on PCs. Basically, it's all in the clear. So, doesn't matter what the password is, it can be seen. So in the 20 minutes available for the presentation, obviously we can only just starting to scratch the surface of some of the complexity in this diagram. But in the few minutes we've got left, maybe just highlight a few important things. So what we haven't touched on yet is this class of devices here. So these are what we call the NIP devices, the non-IP devices. And actually from an IoT perspective, this is going to be the lion's share. These are all the devices that can run on battery for a reasonable amount of time. And the reason they can run on battery on a reasonable amount of time is because they use highly optimized radio protocols, and because they're highly optimized, often don't support IP. So what this then introduces is a whole new ecosystem that consists not just of these mainstream IP devices. There are lots of proprietary radio protocols on the market as well, which are then intermediated by what we've generically called the protocol bridge function. So the Philips, Hue, Signify, I can't remember whatever they're currently branded name, is a class of this, as is Samsung SmartThings Hub, etc. They're bridges. They sit on the IP network. They manage the communication with other protocols out that aren't visible on the IP. And they may make their services available to local applications, or they may communicate directly to the cloud-based services. So a whole rich set of new architectural elements, interfaces, and communication lines, and each of which has its own subtle security constraints and implications. So the second thing I want to draw attention to is these devices. I mentioned them earlier, the IP extenders, very common in households, but also, we've strangely not yet talked at all about the core router. So these are arguably IoT devices. They've got interfaces, but disregarding the semantics of whether you would call them an IoT device or not, from a security perspective, they are absolutely essential in understanding, what current risks exist, because the bits and bytes on the internal network are being funneled, almost all of it's going through the core router, and arbitrary subsets are going through extenders you've got moving through the house. But as we just mentioned a while ago, these management interfaces here, these IP management interfaces, are often insecure in their own right, and as such, it becomes the largest security threat to the system. So by way of summary, here are the key takeaway actions from my perspective. So we've only really just scratched the surface here, but what I've hoped to try and get across to you there is a need for much more sophisticated modeling of the attack surface. Better understanding, better common understanding of this is only going to come through better communication, which requires this sort of like more sophisticated, better agreed set of models. And again, the better we understand the problem, then the better that we can construct the mitigations. And full disclosure, one of the fundamental underlying tenets of the Many Secured project is of fundamental belief that the gateway or new forms of gateway have a substantive role to play here. Second point is there's a lot more detailed information on what I've just discussed, both on the Many Secured website, and I think shortly a lot of the work here has been done by Kubilai from Oxford University, and there's going to be some academic papers published on this same subject. But if you want to get a quicker hands-on, just as a heads up, on the 4th of December in the tutorial sessions, we'll be doing an hour-long session covering this topic, but going much deeper into what the potential sort of like mitigating strategies are to the various attacks that we've discussed. But in the interim, if you want to contact myself, so it's like Nick at Nquiring Minds, feel free to contact me, and of course, ask any questions of me in the next few minutes. Thank you.